Hello dear students, welcome in today's class. Today we are going to begin with the very first chapter of class 12, that is electrostatics. But before we start, let me remind you again that whatever chapters or concepts you have learnt in class 11 were exactly the same that you have learnt in class 9. So now you can understand that whatever we are going to learn in class 12 are going to be the same concepts that you have learnt in class 10th. So now try to recall, what all chapters did you learn in class 10th? So you have learnt about electricity, magnetism and light, right? So these are the units that we are going to handle in class 12th as well, that is electricity, magnetism and light. All right. So if you have time, you can quickly revise whatever you have done in class 10 and then start with the class 12th videos, right? So that would really help you to, get started, right? So now put down the heading electrostatics. Okay, so when I say electrostatics, one thing that you should realize that in NCERT, the first chapter of class 12 says electric charges and fields. Okay, and the second chapter is electrostatic potential and capacitance. Okay, electric potential and capacitance. So we are clubbing these two chapters and studying them together and calling them electrostatics. So keep that in mind. So electrostatics, this is going to cover the entire chapter 1 and chapter 2 of class 12. Okay, so when I say electrostatics, what do you think it means? So you would say electro is something related with charge. All right, electro is something related with charge, right? And when we say statics, so of course you understand that it is something when it is at rest, that is static, right? So electrostatics is the study of all the phenomena related with charges at rest. Easy? So far so good. You are able to understand that electrostatics, we are going to talk about charges at rest. Now if I may ask you that what do you mean by charge? Before we start with study of charge, do you know what charge exactly means? You have heard of charge, this word charge, so many times in your previous classes, but do you exactly know the definition of charge? So let me tell you one thing very quickly here, that let's say there is a charge which is at rest. Okay, a charge which is at rest, and rest would mean velocity 0. It creates an environment around it that is called its electric field. All right dear students, that's called its electric field. Just like a mass has its gravitational field, charge at rest will have its electric field. Okay, when we say that there is a charge in motion, okay, and that motion is, let's say, with constant velocity, let's say with constant velocity. Okay, so you would say, okay, charge in motion, that is what current is. So it basically we are talking about charge and as well as current, right? So we will say that yes, there is going to be an electric field associated with it, right? Now there will also be a magnetic field, dear student. Now there will also be a magnetic field. Quickly, let's revise again. When we have a screwdriver and we wound a wire over it, and when we pass a current through the wire, it starts behaving like a magnet. So current has its magnetic effect. That's what you've learned in class 10th, right? So charge when in motion produces electric field as well as magnetic field. Now think about the third case, when charge is in motion, all right, and that too, let's say accelerating, dear students, let's say accelerating charge. Now what happens is, of course it's going to have its electric field, of course it's going to have its magnetic field, but now what extra will it have? It will have electromagnetic waves. Okay, it will have electromagnetic waves associated with it. Do you have an idea? Like light is an example of electromagnetic wave. All right, so far so good. You can understand all this, that okay, charge when accelerating produces electromagnetic wave. That's what we are going to learn. Now very quickly students, so we were talking about what are we going to study in class 12. We said that we'll learn about electricity, we'll learn about magnetism, we'll learn about light. This is what we've learned in class 10th. Now can you realize these are all the study related with charges. So majorly the entire class 12 is the study of charges in one way or the other. So it is now very important for us to actually understand what charge is and how to exactly define it. All right, so but before we start, just put down the heading electrostatics and we'll write these basic things very quickly. Okay, all right, so Write down, electrostatics is the study of charges at rest. Charge, of course, we denote it by Q. As you know, as you might have used, it is an intrinsic property of fundamental particles like electrons, protons, etc., due to which bodies show electric and magnetic behavior as well as attract or repel other charged bodies. So now this definition will make sense to you, that yes, electric charge is basically an intrinsic, the most basic property that we will use to define other properties, but it is such a basic property that is going to define other properties and not defining itself. So it is a fundamental property, it is an inherent property, it is a basic property, whatever you may call it, of fundamental particles like electrons, protons, due to which bodies show electric and magnetic behavior. So whatever electric and magnetic behavior you see is because of charges, right? As well as attract or repel other charged bodies. This is very important, that one force that governs most of the things around us is the force between mass and mass, that is the force of gravitation. But now we will learn one more force, that is the force between charge and charge. By the way, it can be repulsive as well as attractive, where the force between masses is only attractive. Okay, so as I said, very quickly write it down please. Charge when at rest produces only electric field. Charge when in motion with constant velocity produces electric as well as magnetic field. And charge when in motion with varying velocity produces electric field, magnetic field as well as electromagnetic waves. Alright, so you can pause the video and copy it down and then we move forward. Alright. Okay, so the next thing. Also, we will share these slides with you just in case you want it for later reference, but still I would highly recommend that you should make your own notes and do not rely on any printed notes while you're learning, because that will not have the same impact. Okay, let's discuss some properties of charge. Let's say a charge cannot be massless. So this is very important, that charge exists because of, let's say, electron, protons and particles like these will always have mass associated with it. So whenever there is a particle that has charge, it needs to have mass. Or we can say whenever there is a transfer of charge, that will always be accompanied with a transfer of mass. So charge cannot be transferred without any mass transfer. So whenever a body is charged, its mass will get affected. We will understand how. Okay. Like charges repel each other, whereas unlike charges, this is the nature of charge. You know that a neutral atom has equal number of electrons and protons, right? So when we say electron, proton, these are the most fundamental particles that you can think of, charged particles that you can think of course. And it was seen that electron had properties of charge, proton had properties of charge, but when we club them, they lose their properties of charge. Hence, if one particle has a charge in positive fashion, then the other needs to be defined in negative fashion so that they neutralize. That is what we can say. So we therefore will now say that, let's say, electron is a negatively charged particle, which you of course know, there's no logic, it's just a convention, and proton has a positive charge. So electron we denoted by what? E minus or minus E, okay, and proton is like plus E. So these are the two most fundamental charge particles that you of course already know. But now if everything is consisting of equal number of electrons and protons, that is why everything around us which is made up of electrons and proton is still neutral, because electron and proton cancel out each other's charge, right? So now if you have to make anything charge, what do you need to do? You need to create this imbalance of electrons and protons. But this imbalance can only be done by removing electrons or adding electrons. Of course, you know that protons are very much immune inside the nucleus. We cannot change the proton, we cannot transfer the protons, we can only transfer the electrons. Okay, so very quickly, if we have excess electrons, so like if we add electrons, right, then the body will set to acquire negative charge, just like chlorine minus, right? So chlorine, if adds, we add an electron to it, of course you understand this called, it's anion, then it's going to be like a negatively charged body. And can we also say that mass will slightly increase, even though slightly, but it will increase, right? And what about if there is a deficiency of electrons, if we remove electrons from a body, from an atom or whatever it is, then it will be acquiring positive charge. So positive charge is not coming because protons are coming, it's because electrons are going, right? So for example, sodium would become sodium plus, and the mass is going to decrease. Keep that in mind, even though slightly, but yes, it's going to change. Okay, next thing. So if we remove electron from an atom, it becomes positively charged. If we add electrons to an atom, it becomes negatively charged, right? A body can acquire charges by processes like rubbing, conduction, induction, photoelectric emission, and all these things. So we will study about that, don't worry. But for now, you can just copy down the important stuff, then we move forward. Students, again reminding you, class 12th, you will have lesser time to study. So make sure you study everything in very much detail and with utmost sincerity. One more thing, that 11th physics was mostly about things you were able to visualize, like a block of mass, right, some mass, or let's say water flowing, you were able to see those things. But electromagnetism is like of particles, of subatomic particles, which are very tiny particles, which you cannot see in day-to-day life. So that makes things a little difficult, because mostly physics is about imagination, but the imagination won't go well in electromagnetism. So you will need to be a little more, alert about things, what I am telling, the examples that I am taking. So these will definitely help you. So you cannot just rely on the basic vocabulary, but also try to relate things with the day-to-day life, right? Okay, so if you've copied this down, we move forward. Next. So charge is of course a physical quantity, it is a measurable quantity. So whenever we talk about a measurable quantity, a physical quantity, the next thing that comes to our mind is that we should also talk about its various units that are prevailing. So that's what the next heading is. Put down the heading, units of charge. Okay, right. So when we say units of charge, so the first unit that of course we would want to discuss is SI unit, and that is of course Coulomb, that you might have learnt in your previous classes. The next common system that prevails is CGS, which was before SI system. So SI system is the latest system. Before this, there were two different units of charge, one related with statics, the other related with dynamics. So right now we are studying statics, where charge is in motion, where charge is at rest, sorry. And dynamics would be when charge is in motion. That is where magnetism will come into play. So that is why there were two units. First, electrostatic unit, and the second is electromagnetic unit, ESU or EMU. So if you can realize what is the conversion factor, 1 coulomb is 3 into 10 raised to the power 9 ESU. So that's like huge. 1 coulomb is huge as compared to ESU. In fact, coulomb in general is very huge. That is why even if we have SI unit as coulomb, mostly what you will come across is millicoulomb, microcoulomb, nanocoulomb, picocoulomb, etc. So when I say millicoulomb, I hope you understand that this prefix would mean 10 raised to the power minus 3, micro would mean 10 raised to the power minus 6, nano would mean 10 raised to the power minus 9, and pico would mean 10 raised to the power minus 12, right? So 1 coulomb is 3 into 10 raised to the power 9 ESU. You want to convert ESU to coulomb, you can of course do that. 1 ESU is going to be 3.33. Of course it's going to, yeah, so 1 ESU is going to be 3.33 into 10 raised to the power minus 10 coulomb. Similarly, EMU, 1 coulomb is 0.1 EMU. So 1 EMU is going to be 10 coulomb. So keep these conversion factors in your mind. These are going to be very important, right? So yeah, note this down, then we move forward. Okay, so after you are knowing ESU, EMU and SI, you completely now know SI system and CGS. But can you think of other units of charge that you see around, the practical units of charge that you might have come across? So these are two units that you need to know. These are the practical units of charge. One is ampere hour, we also call it amp hour. So you can understand what it should mean if you know the formula that current is Q by T. In fact, when I say that current is charge flowing per unit time, one more thing that comes to my head is that if you realize charge is not a fundamental quantity, current is the fundamental quantity. So charge is of course a scalar quantity, it does not have a direction, and it is a derived quantity, my dear students. It is a derived quantity. Keep that in mind. So Q is equals to IT, right? So what are going to be the dimensions of charge? So you would say AT, right? The dimensional formula of charge would be AT. It is a derived quantity. One more thing, my dear students, what is that? That if I have to just write 1 coulomb is 1 ampere into 1 second, isn't it? 1 coulomb is nothing but 1 ampere current passing for 1 second will transfer a charge of 1 coulomb, right? So now you can understand what should be 1 ampere hour. So 1 ampere hour would be 1 ampere into 1 hour, or we can say that amount of charge transferred, right, when 1 ampere current is passed for an hour. So if 1 ampere current is passed for an hour, then the amount of charge that is transferred, you have come across this term whenever you are specifying the capacity of a battery. Think of the battery of your mobile phone. So you would say that we have come across the term milliampere hour, mAh. So milliampere hour is this only. So if 1 ampere into 1 hour is like 1 ampere into 3600 seconds, my dear students, and 1 ampere into 1 second is 1 coulomb, so this is going to be 3600 coulomb, right? So 1 ampere hour is 3600 coulomb. Now if 1 ampere hour is 3600 coulomb, what should be 1 milliampere hour? So you would say divided by 1000, so that would mean 3.6 coulomb. So that is why when we say a battery is having a higher capacity, that means it can store more charge. That means it will take more time for it to get charged and to get discharged, and that is why we will say its capacity is higher. So we always specify the capacity of a battery in terms of the charge it can store, and it is normally specified in milliampere hour, and for electric cars and electric bikes, now they are specified in AH, that is ampere hour, right? So 1 ampere hour, now you should be knowing, is 3600 coulomb. One last thing, Faraday. So Michael Faraday, the greatest of all time, he discovered the phenomena of electromagnetic induction. The first generator ever constructed was by him, and that is why we can thank him always for commercialization of electricity. So whatever advantages of electricity that we are making of today are all because of Mr. Michael Faraday. So he is, someone who has really changed our lives. So do respect him, and he gave a unit of charge because he had a lot of things to do with cells and stuff like that, and that is where charge gets transferred. So let's discuss that. What is that unit? So of course that whenever we talk in terms of particles being transferred, we talk in terms of moles, right? So when we talk in terms of mole, so what I need to do is that I need to explain that 1 Faraday therefore becomes quantum of charge on 1 mole electron. So he said that, okay, let's make a unit that is equivalent to 1 mole transfer of electrons. Okay, and now you understand that 1 mole is like 6.022 into 10 raised to the power 23. That is like the number of electrons that you will transfer, multiplied by 1 electron's charge, which I am writing, I hope you know it, and we will discuss in the next slide, is 1.6 into 10 raised to the power minus 19. So when you do that, you will get 96,500 coulomb, the biggest unit of charge that you are seeing around. So whenever now we will say 2 mole electron has been transferred, you will understand that 2 Faraday charge has been transferred. It can be positive or negative depending on electrons are gained by the system or lost by the system, right? Copy this down, then we move forward. All right, so once you are done with this, let's talk about the fundamental particles that you will come across. So of course you know a little about them already. So there is proton, there is electron, and there is neutron. So proton, you understand the charge is this, we denote it by E. Then electron, the charge is like same but negative, and neutron is 0. Alpha particle is approximately like, you can take it as like helium nucleus. So helium nucleus is basically a combo of 2 protons plus 2 neutrons, my dear students. So if that is the case, neutron do not add to the charge, so it is only the proton, so its charge is 2e. What about the mass, students? So mass of proton, it is almost same as neutron. So let's write it as m. Then this is also approximately m. Neutron is slightly heavier. Electron are very lighter. You of course know that. So this is 9.1 into 10 raised to the power minus 31 kilogram. By the way, this can approximate it as m by 1831 or 1836. So we can say that electrons are approximately 1800 times lighter than proton. They might look equal in magnitude about the charge, but their mass is way less as compared to protons. And what about helium nucleus? So it is approximately 4 times mass of proton because it has 2 proton and 2 neutrons, right? Take a screenshot of this, then we move forward. All right, dear students, so the next thing now is the various properties of charge. So you would say that we have already discussed it, that charge is of 2 types, positive and negative, or we can say like charges repel, unlike charges attract. These are all properties of charge. But if I have to say that what is written in NCERT, what are we going to write in the board exams? If we are going to appear for the board exam, then what are we going to write there? So these are the 4 properties that you should preferably write. So the first is charge is additive. Now, what does it mean? You will write down as I say the definition. So you can write down just that the total charge of a body or a system is equal to the algebraic sum of charges on its constituent particles. So for example, if I tell you that this is any system and it has multiple particles, then the total charge of the system will be the algebraic sum of the charges on its constituent particles. Of course, yes, that is why atom becomes neutral, because when we add charges of protons and electrons, they ultimately cancel out and become 0, right? The next thing, charge is conserved. Of course, you know that even though you might have come across the word that, oh, there is a charge appearing on the body, but charge cannot appear, charge cannot destroy. If charge is appearing on a body, that means someone has transferred to that charge to the body, right? So what do we mean by law of conservation of charge? Please write down, as I say, write down that for any isolated system, isolated means no one is interacting from outside. For any isolated system, charge can never be created or destroyed. It can only get transferred from one part of the system to the other. I will repeat. For any isolated system, charge can never be created or destroyed. It can only get transferred from one part of the system to the other, right? So for example, if I tell you that, okay, there are 3 particles A, B and C, and let's say A has 3 microcoulomb, B has 2 microcoulomb, and let's say C has 1 microcoulomb. So what is the total charge of the system? Of course, it is 6 microcoulomb, right? And let's say if we allow a charge transfer between them, then let's say A has a charge of 4 microcoulomb, okay, and B has a charge of, let's say, 3 microcoulomb. And if I may ask, what is the charge on C? So you can take it like that. Or let's take another example, that let's say there is A, there is B. Very quickly, though very basic, but today's class is obviously very basic because we are just starting off with this new unit. Again, A and B. So this is like 2 microcoulomb and this is like 3 microcoulomb. So the total charge is going to be 5 microcoulomb, right? And let's say if I tell you that A has transferred 5 to B. Now, is that possible? Can you take out 5 microcoulomb out of 2 microcoulomb? Yes, because charge can also go in negative. Then A will have minus 3 microcoulomb. So of course 5 is taken out, and B will have 8 microcoulomb. So it might just feel that, oh, B has acquired some charge is appearing on it, and A has been destroyed some charge from A. But ultimately charge is not being destroyed or created, it's only a transfer, because the total still remains intact as 5, my dear students, right? So that is what law of conservation of charge is. We also use this concept in balancing chemical reactions, and I hope you've already done that. We'll also do that in nuclear reactions now. Okay, so that is going to be a part of modern physics that we are going to learn. So much to learn, very exciting. You need to be on your toes and try to wind up everything. Once it's done, revise and wind up the class so that next time you can clearly relate with the things. Don't keep much baggage for class 12 because you have a lot to do in class 12. Alright, so if I may ask, what is the charge on C? So you would say whatever has happened between A, B and C, it's all right, but the total charge will remain conserved. So if it was like 6, so it should remain 6. So 4 plus 3 plus Q should still remain equal to 6, my dear students. So that tells me that Q is equals to minus 1. So if A, B, C are intermixed, then probably C will have a charge of minus 1 if this configuration is to be maintained, right? So that's about law of conservation of charge. We've written both the definitions. Copy down this and then we move forward. All right. Next, charge is invariant. Now, what do you mean by that? Charge is invariant. So charge is invariant would mean that the value of charge does not change with anything. It does not change with frame of reference. It does not change with temperature. It does not change with motion. On the contrary, most of the physical quantities change for some reason. You have learnt in your class 11th, let's say the weight of a person. It's different on the poles, it's different at the equator. If you go in water, your weight becomes less. You in apparent weight in a lift, that also changes. Similarly, if you talk about motion, speed, velocity, acceleration, these are all relative from different frame of reference. You feel that the value of speed, velocity and everything is different, right? But let's talk about, let's say, let me take an example of mass. What about mass? So some of you might wonder, no, mass never changes. Mass of a body is fixed. You go on the moon, mass is still the same, right? You go on the poles, you go on the equator, you go inside water, mass is still the same. But you know, if we go by the relativity, by the modern physics, if we go about the subatomic particles, even mass varies. So I don't know how many of you have seen this formula. Like we do know that Einstein, the great Einstein, has told us that time is relative, there is length contraction, time dilation. So there are so many things. But even mass is relative, dear students. So this is the rest mass of the body. So when any body is in motion, its mass also changes. But it changes so minutely that we almost ignore that. But if the subatomic particles like proton, electron, when they travel approximately very close to the speed of light, then this factor becomes substantial and the mass changes a lot. So even mass is like varying quantity, but charge on a body does not change. So please write down, charge on a body does not change with motion, medium, temperature, etc. With temperature, you know, the length of this pen, this can't be fixed. In summers it's going to be different, in winters it's going to be different, right? So that's what thermal expansion is. But the value of charge does not change with medium, motion, temperature, etc. Right? That's the third property. Now let's talk about the fourth property, that charge is quantized. Now, what do you mean by a quantized quantity? You've learnt in class 11th photoelectric effect that light is quantized. That is where this term was very much came into being, and you came across this term that light is quantized. It has photons which consist of the energy packets and stuff like that. So whenever anything is quantized, it's like it can only acquire those discrete values. For example, this pen, this is the simplest example. You can bring one pen, then you can bring 2, then you can bring 3. It doesn't mean that you can bring like 2.5 pen, because it won't make sense. So whenever anything is quantized, it's like it can only acquire certain levels and then it will jump on to the next level. That is what quantized quantities are. So charge is of course quantized because you do understand that it is existing because electrons and protons are, or whatever it is, like electrons are being gained or lost, but it has to be in terms of electron. So let's say if there is a neutral body and it has to acquire charge, so you would say, okay, you take out an electron from it, then the charge that will appear on it is going to be 1.6 into 10 raised to the power minus 19 coulomb. If you take out one more electron to give it more charge, then straight away it will be 3.2 into 10 raised to the power minus 19. If you take out one more, then it is going to be 4.8 into 10 raised to the power minus 19, my dear students. If you take out one more, so what are you learning here? That charge on the body is only jumping from this value to this value, this value to this value, and it cannot acquire values in between. So for example, it cannot acquire a value of 2 into 10 raised to the power. That's not possible. Charge will only exist in multiple of E. That is the most fundamental charge which exists independently. So listen to this term very carefully, independently. So maybe in combined state we have found more particles which are even smaller than electron proton, but they have not been isolated. There is an experiment going on, I don't know if you've heard of it, Large Hadron Collider near Switzerland, where scientists are trying to, accelerate proton. It is a huge particle accelerator, 22-kilometer circumference. So protons are being collided to, dismantle them and see the inner particles. So it is, in future this theory might change, but for now we will always say that charge on a body always exists in terms of integral multiple of smallest unit or unit of charge that exists independently. All right, my dear students, so I hope you are able to understand this. So can we summarize this by just saying that charge is always equal to plus minus NE, where N means all natural numbers, right? So I've already given the scope of plus minus because electrons can be gained or they can be lost, right? So charge is always in terms of multiple of electronic charge. But this might change in future. I don't know how many of you have heard of the term quarks, right? So these are called hadrons, protons and neutrons. They are built up of quarks. There are many types of quark, like top, bottom, up, down, sham, strange. So whatever this is, like, there are particles. So even people used to believe that atoms are indivisible, but later on we realized no, atoms can still be broken down into electron, proton, neutron. Now we believe, oh, electron, proton, neutron are fundamental particles. No, in future they will also be broken down, and that's what is going on, right? So there is a quark theory, so we can talk about that. Electrons belong to a new next classification of material, which are called leptons. So we are not discussing electrons here, but let's talk about quarks theory. So I'm assuming that only there are two types of quark, though there are anti-quarks as well. But let's say quarks theory, that's like if we believe that there are two types of quarks. One is up quark that has a charge of plus 2/3e, and then there are down quarks which have a charge of minus e/3. So we can assume that proton, let's say, is built up of two up quarks and one down quark. So two up quarks would mean plus 2/3e plus 2/3e minus e/3. So that's going to be like plus e. Can you imagine that? Of course, yes. Okay, neutron, its situation is just like atom. It is neutral, but it has some charged particles in it, for your surprise. So it is like one up quark and two down quark. So plus 2/3e minus e/3 minus e/3, making it down to 0, bringing it down to 0. While electrons are leptons, so they are a different classification. So if you have to just force this theory on electrons as well, then we can say it has 3 down quarks. So 3 down quarks will be minus e/3 minus e/3 minus e/3, making it minus e. Right, dear students? So much learned today about new kind of particles and more about charge, because it's very compulsory, very important, because this is the hero of class 12. The entire story of class 12 revolves around the story of charge, right? Alright, very quickly then. So 11th was majorly discussing about mass, and 12th is majorly discussing about charge. So in the end we will also classify or just differentiate between charge and mass very quickly. This question very quickly: if 10⁹ electrons move out of a body to another body every second, how much time is required to get a total charge of 1 coulomb on the body? This question will make you respect 1 coulomb. So imagine, per second you are taking 1 billion electrons out. Per second you are taking 1 billion electrons out. Okay, so how much time will it take for it to acquire 1 coulomb charge? So can we say 1 billion is like 10⁹ into 1.6 into 10⁻. So you have to try the question first. Pause the video, try the question first, then go for the solution. But I am not waiting here. I am just starting with the solution. So this much coulomb is being transferred per second. All right, so you understand that. So how much time will it take to transfer 1 coulomb? So you would say 1 over this much seconds, right? So when you solve this, this will be like 6.25, right? So this is like 1 over 1.6 is like 0.625, and this is like 10 raised to the power 10. So let's make it 10 raised to the power 9, right? This much second, right? 6.25 into 10 raised to the power 9 seconds. Seconds look like a very small unit for this. It is almost like 6.25 billion seconds it takes for this. Imagine per second you are taking out 1 billion electrons. Still you keep on doing this for this much second. I will make you realize how much time this is. So let's say this time is 6.25 into 10 raised to the power 9, and I divided by 3600. So this will convert it into hours. Very quickly, let's divide it by 24. This will convert it into days, right? And let's divide it by 365. This will convert it into years. So you will realize that this is approximately 198 years. It will take approximately 200 years for this activity to be continued to acquire this 1 coulomb charge. It's a huge charge. You can never imagine 1 coulomb charge around you. That's a crime. You cannot imagine 1 coulomb. 1 coulomb is a huge charge that is not possible, that cannot be available, right? Try the next one. Okay, how much positive and negative charge is there in a cup of water? So a cup of water, it might be neutral. We are just trying to figure out how much positive and negative there is. Okay, so I took water, let's say 180 ml. So you would say the number of moles of water in this is going to be 180. By the way, the density of water is 1 gram per ml. So 180 ml will also mean 180 gram. You divide it by 18, that is the molecular mass of water. I hope you know that. Oxygen is 16, hydrogen 1, so 18. So it's like 10 moles. Okay, but in every number of electrons or protons is going to be not 10 mole, but 10 into 10 mole. Tell me why? 10 into 10 mole. Why? Because in every water molecule there are 10 protons and 10 electrons, 2 because of hydrogen and 8 because of oxygen. So it's like 100 mole. Okay, so there are 100 mole electron proton. So how much charge is it going to be? So you remember 1 mole electron is like 1 Faraday. So the amount of charge that this will have is going to be like 100 Faraday, my dear students. 100 Faraday. Can you imagine? But you don't feel that charge. When you drink this water, you don't feel this much charge has gone into your stomach. Why? Because it's plus minus combined. You cannot imagine them to be separated. So separated form charge 1 coulomb, very big number. But combined form charge 1 coulomb, very easily available, right? But this does not count as charge because effectively the net charge is 0, right? So 100 Faradays approximately, you understand now? So it's like 100 into 96,500 coulomb. It's going to be like 96,500, right? That's like 96,50,000 coulomb, approximately 1 crore coulomb, or you can say like 96 million, whatever, right? So I hope you've understood whatever I was trying to suggest here. And now let's move forward. Now let's move forward with the next question. Okay, yeah, 9.6 million. Fine. Okay, so copy this down, then we move forward. Okay, so finally we'll end today's class just by stating the difference between charge and mass. Charge can be positive or negative, mass can only be positive. Just brushing up with what we've done. This is class 12th, this is class 11th, right? Charge can attract or repel, mass can only attract. Charge cannot exist without mass, but mass can exist without charge. Photons do not have any rest mass, so no charge on them. Charge is invariant, mass can vary. Charge is quantized, mass is like something we cannot say it's quantized. We don't know the level of quantization of mass, right? Physics will need to evolve way more to understand the quantization of mass. Thank you so much, dear students. I hope it was a good start of class 12 and you were able to understand 3 main things today. That is the definition of charge, the units of charge, 5 units, Coulomb, ESU, EMU, ampere hour, Faraday, and then the main 4 properties of charge, what exactly they mean. This gives us a strong foundation to understand things further, and we'll keep coming up with such classes to wind up the syllabus of class 12, simultaneously do all sort of numericals that you can be asked related with JEE, NEET or any board exam. Right, students? Thank you for your time. Keep working hard, make your parents proud, and I will see you soon. Bye.
If you enjoyed this video, please don't forget to like, share and subscribe to our channel.